In our modern world, bacteria aren't just microorganisms. They're silent threats lurking in our everyday lives. Bacterial infections can strike anyone at any time, and often, antibiotics are our first line of defense. But here's the hard truth. Bacteria are evolving, finding new ways to outsmart our medicine. In the United States alone, the CDC estimates that 2.8 million people are infected each year with antibiotic-resistant bacteria. Moreover, overuse, misuse, and abuse of antibiotics in human medicine, agriculture, and livestock continue to be contributors to the acceleration of bacterial resistance. According to the World Health Organization, antibiotic resistance is one of the biggest threats to global health today. The consequences are dire, leading to longer illnesses, higher mortality rate, and overall economic burden for everyone. Here I present my project on creating a novel strategy for modulating the antibiotic response and growth behaviors of various gram-positive and gram-negative bacteria through the use of oscillating compound magnetic fields. So before we get into my project for this year, let's talk a little bit about why I decided to choose this topic. Over the past years, I've developed an interest for magnetic fields, creating my own inductor-capacitor circuits and finding new ways to test with power transmission. Last year, I got an interest in biology, and I mixed my two new interests to create a project on assessing the effect of square-wave magnetic fields on the growth behaviors of E. coli, which is a gram-negative bacteria. My project had developed some very interesting results, so I decided to expand on that topic, now testing for both gram-positive and gram-negative bacteria, and also now testing for antibiotic resistance. So, research has already proven that magnetic fields do have an impact on bacterial behaviors, and it has been determined through multiple studies that bacterial cell viability decreases as the amount of exposure from magnetic fields increases. Additionally, it was determined that pulsed electromagnetic fields have an impact on the antimicrobial properties of bacteria. Although I'm not working with pulsed electromagnetic fields, I believe that I can apply the same principles to my project, which is now to test whether I can see whether I can modulate the bacteria using magnetic fields, which leads me to my hypothesis. I hypothesize that magnetic fields can be used as modulators for manipulating bacterial growth behaviors and antibiotic resistance. Now let's get into my experimental design. My experimental process followed four main stages. The first stage was deciding what kind of experiment I want to be working with. I already had four different waveform types, which I used for each of my experiments. First, we had a sine wave, a sync wave, and two complex waveforms, which I generated on my own. I'll get into that a bit later. Additionally, I had five bacterial types that I was working with. I had E. coli K12, Bacillus subtilis, both of these are gram-negative by the way, and I also had Staphylococcus epidermidis, Clostridium sporogenus, and Enterobacter aerogenes. Those three were gram-positive. On top of this, I also decided field strength, but later in my experiment, I decided that I wanted to use a constant field strength for each of my experiments, so I decided on using a field of 300 microtesla. Now, let's get into stage 2. Stage 2 was the treatment phase, and in it, I had to place my bacteria inside of my incubator shaker setup in order to expose them to the magnetic fields. The magnetic fields were produced by this solenoid coil, which should be calibrated before each and every single experiment. You might be wondering how the control bacteria wasn't exposed to any of the magnetic fields while the exposed group was. To answer this, I used a ferromagnetic shield, and this shield would basically protect the control bacteria from all the magnetic fields being produced by the solenoid. Let's get into stage 3 now. In stage 3, I had to measure the growth behaviors of both the gram-positive and gram-negative bacteria. In order to do this, I measured the turbidity of both groups periodically at different increments during the experiment. The turbidity is basically the bacterial concentration within its growth medium, and this is how I would calculate which group was growing at a higher rate and which group was growing at a lower rate. The fourth stage was when I treated the bacteria to the different antibiotic groups. I used 3 antibiotic groups: ampicillin, penicillin, and streptomycin. And in this phase, I would basically plate the bacteria, and then using a modified version of the Kirby-Bauer method, I would basically be able to incubate the bacteria after plating them, and then measure the inhibition zones produced by the antibiotics, as visible in this diagram here. So now let's get a bit more into the waveforms, which I used during my experiment. We have 4 waveforms that you can see here, and let's get into the first waveform. This is my sine wave, and it was administered at 50 Hz. Here's my sync wave, which was administered at 50 Hz as well. My 2 special waveforms, which I created on my own, were administered at 15 Hz each. But let's see how all of these differ. As you can see, I used the fast Fourier transform, which was a method in which I could analyze the independent and natural frequencies of all of these waveforms. The sine wave is angular around 50 Hz, meaning that its natural frequency is staying around the 50 Hz range. However, the sync wave has a natural frequency domain of 50 to 250 Hz. And although administered at 50 Hz, this is the natural frequency that my bacteria was being exposed to. My special waveforms are in a bit more of the higher ranges, with their frequency ranges being from 50 to 600 Hz, and with my special waveform 2 having a frequency range of 400 to 550 Hz. Each of these different waveforms had different impacts on the growth behaviors and antibiotic resistance of the bacteria, and I'll get into that in my results. Here's a graph representative of my data. We can see that in this chart, there are 4 columns and 3 rows. Each of these columns represents the different waveform that the bacteria is being exposed to, and each of the different rows represents the different antibiotics that the bacteria was being treated with. In the individual graphs, we can see that there are multiple bacterial groups at the bottom, and with each of these bacterial groups, there are 2 columns. The red column represents the control bacteria, and the blue column represents the exposed bacteria. And basically, these columns are representative of the inhibition zones of each of these bacterial groups. And the higher the inhibition zone, the higher the impact of the antibiotic on the bacteria. Similarly, let's look at the different impacts of the waveforms on the turbidity of the gram-positive and gram-negative bacteria. Turbidity, to rephrase, is the concentration of the bacteria within its growth medium. And this is basically how I measure whether the exposed group has more bacteria or less bacteria compared to the control group. In the graph to the left, we can see that it's an analysis of the turbidity change in E. coli. And in this graph, we can see that there's a red line, which is flat, and a bunch of different other colored lines. The red line represents the turbidity of the control group, and the different colored lines represent the turbidity of the different waveforms bacteria that the bacteria are being exposed to. Now, the way to interpret this is, if the waveform's turbidity line goes above the red line, that means that the bacteria is having stimulating effects, as it is higher than the control group. However, when the other colored lines dip below the red line, that means that the waveform is having inhibiting effects on the bacteria, as the turbidity is less than the turbidity of the control group. We can see that for gram-negative E. coli, the lines generally start below the control group, showing that it has inhibition effects from the start. Conversely, in the graph to the right, we can see that in Staphylococcus epidermidis, the different waveforms generally start off with stimulating effects on the bacteria, as they start well above the control line. But throughout the duration of the exposure, they generally go on a downward slope, eventually dipping below the control group, ending off with inhibiting effects. Now, in my results portion, I took a comprehensive study of both my antibiotic resistance and turbidity graphs and put them all onto one table chart. So in it, we can see that there are 4 columns. The first column represents the antibiotic group, the second column represents the bacteria group, the third column represents the antibiotic susceptibility, and the fourth column represents the growth behavior. In the first 2, we can see that it's an analysis of streptomycin with the sync wave on gram-positive and gram-negative bacteria. In both of them, the antibiotic susceptibility of the bacteria decreased, with streptomycin having a higher impact on gram-positive bacteria, 59.4%, compared to gram-negative bacteria, which was only inhibited by 8.3%. However, in the third one, ampicillin on Staphylococcus epidermidis with the sync wave, its antibiotic susceptibility was boosted by 118.75%, as the sync wave had the highest impact on Staphylococcus epidermidis. Similarly, with penicillin on Staphylococcus epidermidis, the sync wave had an increase on its antibiotic susceptibility, increasing it by 20%. A general trend in this graph is that the growth behavior always ends up decreasing for the waveform's exposed bacteria, but the antibiotic susceptibility has a chance of increasing or decreasing, generally increasing the antibiotic susceptibility from each waveform. To conclude, the outstanding influence of magnetic fields in both gram-positive and gram-negative bacteria's antibiotic susceptibility and growth behaviors was confirmed during the experiment. The results were recognized within hours of exposure from the fields, but the field's impact degraded as the amount of exposure increased. The sine wave had the least impact, and the sync wave had the most impact, generally decreasing the bacteria's resistance to the antibiotics. However, my work doesn't end here. As shown in my results, the sync wave was able to significantly decrease Staphylococcus epidermidis' resistance to streptomycin, penicillin, and ampicillin. Those results inspired me to create a working physical prototype of a device that uses a magnetic field technology to treat skin infections caused by Staphylococcus epidermidis. I've already created the initial prototype, but it still has a long way to go. By doing further testing to match the circuit's impedance, as well as by working to redirect the magnetic fields, I believe that I'll be able to create a working model soon, which I plan to develop even further. My work in this project is a testament to magnetic fields' usefulness and versatility in various applications. Thank you.